Assalamu alaikum. That is our lecture number 4. We are going to start with the lecture number 4 for the classical mechanics, and you know that that we have started with Newtonian mechanics for your semester BS 5th and course code PHY 509. Now students, we have previously discussed about the introduction of classical mechanics and what is mechanics and which rules are followed in mechanics, and what is the history of mechanics, and in which branches mechanics is divided: classical mechanics, quantum mechanics. Depending upon the nature of particles or systems, the mechanics is divided as in two ways. First is the classical mechanics and the second is the quantum mechanics. Classical mechanics deal with the particles which are in macro in size, and the quantum mechanics deal with the particles or systems that are micro in size. So now we know that classical mechanics obey the Newton's law. Quantum particles also obey the Newton's law, but for quantum particles they are modified for the particles for the subatomic level or atoms or neutrons. So for continuing our lecture, we are going to start further for the classical mechanics. In Newtonian mechanics, in second chapter, in second lecture we studied that about frame of reference, what is frame of reference, and the time coordinate in the system. We know that for this we need four coordinate system, that is a space time coordinate system, and x y z with the time coordinate is associated. Now for going further, we have some kind of examples for the inertial and non-inertial frame of reference, and that we studied that earth is also inertial frame of reference, and we studied about some inertial examples and some of the non-inertial frame of reference examples in which pseudo forces or the Coriolis forces were involved. Now moving to the introduction or the objective of the lecture, we have to start that are Now the contents or the objectives being learned in the chapter are the conservative field of force and grad u, gradient of u, that is a scalar. Show that force is equal to minus grad of u. Then we have to study about the conservation theorem of energy and have to prove for that either the energy remains conserved. Then, as we discussed previous about the system of particles or the single particle, now we have to discuss about the mechanics of the system of particles and what kind of forces are applied on the particles, that are the external forces and the internal forces. At last we have some references of the lecture. Now starting with the conservative field of force, we know that in a closed path the work done or the field force remains conserved. It means that the work done in the field is zero. So here we can say that you can see there is a path from 1 to 2 and 2 to 1. So we can say if the work done in a closed path is 0, that is called a conservative field, means that there is no change in the energy or the work done is same. So the examples are the gravitational field and the electric field. Here we can write work done is equal to closed integral of f dot dl. That means that line integral is converted into closed path integral, and that is integral of closed path f dot dl is equal to 0, means the total work done in the closed path is 0. Mathematically the curl of a vector should be equal to 0. So if we take work from 1 to 2 is w1 and from 2 to 1 w2, that means the total work done in that path will be equal to 0. Now the second definition can be said that if the field said like that, if the field force is such that the work done from w1 to w12 on the particle is same for the any physically possible path between 2 points 1 and 2, then the force field is said to be conservative. It means that work done from 1 to 2 and the work done from 2 to 1 will be mathematically 0, and so we can say that the field is force is 0. Mathematically the field is conservative, so it can be written as closed integral as f dot dl is equal to 0. You can write the definitions and understand the definitions written here. With the definition or with the formula written before, understood before, we can say that physically it means that in a non-dissipated field, energy means that where the energy is not uh, dissipated or lost. spent in a moving particle from point 1 to 2 is equal to the energy gain in bringing the particle back from 2 to 1. Thus, the net change in the energy in a closed path loop is 0. If a dissipated force as a friction is present, then F dot dl is always positive. It means that if there is a dissipative force such as friction, then there will be energy loss, so F dot dl will be positive. It means that if F dot dl is positive and friction is present, it means there should be done an extra work to overcome the frictions. So energy will the loss of energy will covered with that of the external with that of the extra work done on the system. Now, applying the Stokes theorem as we have written previously, uh, in closed integral f dot dl is equal to 0, then that is equal to surface integral curl f dot and ds is equal to 0. So we can say curl of f is equal to 0. Here the line integral is not a line integral, but it is a closed integral with a circle on an integral. Now, for the definition of grad u del u, that is a scalar, grad u is the maximum increase of a scalar at any given point along a particular field. Grad u is a vector quantity. Here u is a scalar quantity. When a grad is applied on it, then that scalar quantity is converted into a vector quantity. It means that if a scalar amount is or the magnitude is tend to increase, and grad is applied on it, which is a vector quantity in a particular field, that gives a specific kind of value in a vector form in specific kind of direction. The value of grad is equal to partial over partial x I cap plus partial over partial y j cap plus partial over partial z k cap. Now to show that force is equal to minus grad of u, we will take a scalar point function. Then we can write the value of del operator, that is equal to partial over partial x I cap plus partial over partial y j cap plus partial over partial z k cap, and here u is a scalar, that is equal to u. So applying the operator on the u, that is grad u is equal to del u, that gives partial u over partial x I cap plus partial over partial u over partial y j cap plus partial u over partial z k cap. Now taking the curl of a grad u, we have written here the value of grad u, and we have discussed about the curl of taking a curl of a vector. We can write curl of grad u, the above mentioned value. We can write partial over we can write in the determinant form I cap j cap k cap, and below it we can write partial over partial x, partial over partial y, and partial over partial z, and below it we will write the value of grad u, that is partial u over partial x, partial u over partial y, partial u over partial z. The value of the curl is also the del operator value, partial over partial x, partial over partial y, and partial y over partial z. So now calculating the curl of grad u for the one component of x component, that is equal to I cap into partial over partial y into partial u over partial z minus partial over partial z into partial u over partial y, then multiplying the partial over partial outside the bracket inside the bracket, and that is equal to curl of grad u of x component is equal to I cap into partial square u over partial y partial z minus partial square u divided by partial z partial y, and that is a perfect partial on both sides. So that is equal to partial square u over partial y partial z is equal to partial square u over partial z partial y. Then that two partials are equal, so the above value is equal to 0. So we can write curl of grad u, that is equal to 0. If that is equal to 0 for the x component, then that is also equal to the that is also equal to 0 for the y and z components. So we can write similarly the y and z components are equal, so that the three components value is also equal to 0 for the curl of grad u. It means that when you apply a gradient on a scalar component, that is converted into vector, and when the vector is quantity is again multiplied, or to cross product with the vector quantity, that is equal to 0. That we have discussed that the cross product with the same vector cannot be taken, so that is equal to 0. So here the curl of grad u for the three components is also equal to 0. So here curl of grad u is equal to 0 in equation 1, and from the previous equation, from the previous equation, for the conservative field of force F, and we have written that curl of F is equal to 0. So equating the two equations 1 and 2, we get that curl of F is equal to curl of grad u, and that is equal to force is equal to grad of u. In order to give a scalar function of physical meaning, we sign a negative sign on it, then that gives F is equal to minus grad of u. The that is the equation we have to prove that force is equal to minus grad of u. Now to calculate curl of conservative force, we will write to calculate the conservative force mathematically. First of all, we can write curl of F is equal to del cross F. Now here del is the operator. Giving it equation number 1, then writing the value for the force vector F is equal to minus grad of u. We know that force is negative gradient of potential energy. Giving it equation number 2. Now we have equation number 1 and 2. We will compare equation number 1 and 2 and substituting the value of force in our equation 1 from 2 to 1. Here we can see that the two operators are operating. First one is the cross product and second is the dot product. Tension vector, we know that grad is equal to partial over partial x I cap plus partial over partial y j cap plus partial over partial z k cap. Now del u will be equal to partial u over partial x I cap, partial u over partial y j cap, partial u over partial z k cap. Now we have the value del dot u, that means del gradient of u. Now taking the curl of gradient of u, we will have curl of f will be equal to I minus determinant of I cap, j cap, k cap, then writing the values of the operator partial over partial x, as we are taking the cross product partial over partial x, partial over partial y, partial over partial z. Now writing the value for del u, we have this value. We will write partial u over partial x I cap plus partial u over partial y j cap plus partial u over partial z k cap. We write these values under the given unit vectors. Now opening the determinant, solving it, we will get this value I cap into 1 column. We will cross multiplying the two columns j and k. We will get partial square u over partial z, partial square u over partial y partial z, minus partial square u over partial y partial z. Similarly, we will get minus j cap into second row and first column, second column and first row, partial square u over partial x partial z, partial x partial z minus partial square u over partial x partial z partial x minus the first value is plus for the determinant, second is minus, and so the third value that is plus. Now first row, third column left hand cross multiplication, the first two columns, partial square u over partial x partial y minus partial square u over partial y partial x, closing the brackets. That will become ucy minus uyz minus g cap into uxz zx minus uxz plus I cap into uyx minus uxy according to the partial derivatives in the denominator. Using the theorem, we know that uzy is equal to uyz, uzx is equal to uxc, and uxy is equal to uyx. So in above equations, substituting this value gives cancels all the equations as they are both equal terms. So we get for this, for I cap, j cap and k cap, we get curl of f vector is equal to 0. So from this we have proved that curl of f is equal to 0. That means the conservative field of force is equal to 0 in 3 axes x, y and z. That is the required answer.
Conservative and non-conservative forces.
Conservative forces.
Objective: to differentiate between conservative and non-conservative forces. We know that work done by a force is equal to the dot product of force and displacement. Let us look at the work done by two different types of forces, gravitation and friction. Consider an object taken from point A to point B along the curve y of x near the Earth's surface. Let us calculate the work done by gravity when object moves through an infinitesimally small distance dr from a point P on the curve. dr is the summation of its displacement along the x-axis dx and its displacement along the y-axis dy. Gravity acts along the y-axis, so work done by gravity dwg is minus mg dy. The total work done by gravity from A to B is integral of minus mg dy from y1 to y2, which is equal to mg into bracket y1 minus y2 bracket closed. Observe that work done by gravity depends on the initial height y1 and the final height y2, and that it does not depend on the shape of path taken by the object between those points. So, it can be said that irrespective of the path between points A and B, work done by gravity is the same. If the object is brought back to A through another path, as the initial and final positions remain the same, the total work done is zero. Such forces whose net work done in a roundabout motion is zero are called conservative forces. Work done by a conservative force is independent of the path taken. It depends on the initial and final position only. Gravitational force, spring force, and electric forces are examples of conservative force. Now, let us look at work done by friction in a roundabout motion. Consider an object of mass m that is moved very slowly through a distance d between points A and B in a straight line on a rough floor with coefficient of friction mu. The frictional force that exists between the surfaces is therefore mu mg. Friction, as you know, acts opposite to the direction of motion. Hence work done by it is minus mu mgd. Now consider another situation where the object is brought from A to B very slowly along a circular path of radius r. Frictional force along the circular curve is mu mg, and it is opposite to the motion of the object at every point. Hence, work done by friction in this case is minus mu mg pi r. Though the initial and final points are the same in both cases, work done by friction is different. So work done by friction depends on the path taken by the object between initial and final points. Irrespective of the path taken to bring back the object to point A, total work done in the roundabout motion is not zero, as friction acts on the object throughout the path in a direction opposite to that of its motion. Such forces whose work done is not zero in a roundabout motion are called non-conservative forces. When non-conservative forces are at play, energy escapes the system, mostly in the form of heat.
Now, to calculate the conservation theorem of energy, we have a path from 1 to 2, and we have a short path or short patch of dl. So we can write the work done from the path 1 to 2, that w12 is equal to integral for the path 1 to f dot dl, and for that w12 is equal to integral 1 to 2, we write the value of force, that is f is equal to dp over dt, and for that for dp over dt we put the value of momentum p is equal to mv, and mass is constant, so taken out of the differential we can write mdv over dt dot, and dl is the distance. So as s is equal to vt for length, here it is a small patch, so s is equal to dl, and v is equal to dt. We can write in the place of dl as v dt, and uh, calculating this solving this integral, we get that if one if the one component of velocity is within the differential and one is with the dot product on the outside, that is solved as 1 by 2 into d by dt into v dot v. So we can write w12 is equal to m by 2 integral 1 to 2 d by dt into v dot v dt. By solving this, we have w12 is equal to m by 2 into v square, and the closed path integral limit is 1 to 2, and the path limit is 1 to 2. So w12 is equal to, putting the values of the limit, we have 1 by 2 mv2 square minus 1 by 2 mv1 square. So here that is the kinetic energy, that is written as w12 is equal to t2 minus t1. Here t represents the kinetic energy. we have calculated the work done from the 1 to 2 path, that is T2 minus T1 difference between the kinetic energies. Now for potential energy we can write W12 is equal to integral 1 to 2 F dot dl, and from previous equation we know that force is equal to minus grad of u, that is a scalar quantity having a gradient into vector quantity for the force we have written. So we can write W12 is equal to minus into integral 1 to 2 and grad u dot dl. W12, now substituting the value of grad u and dl, we get W12 is equal to minus integral 1 to 2 partial u or partial x I cap plus partial u or partial y j cap plus partial u or partial z k cap dot dl for the value of dl, that is equal to dx I cap plus dy j cap plus dz k cap. Taking the dot product, we know that the dot product for the same component is 1, so we can write partial u or partial x dx I cap dot I cap plus partial u over partial y dy j dot j partial u over partial z dz k dot k. So we have W12 is equal to minus integral 1 to 2 with this all value. Now for as I dot I j dot j k dot k is equal to 1, so we can write W12 is equal to integral 1 to 2 partial u or partial x dx plus partial u or partial y dy plus partial u or partial z dz. Here we know that partial u partial partial x dx plus partial u partial y dy plus partial u partial z dz is equal to du. Substituting this value in the above equation, we get that W12 is equal to minus integral of 1 to du, and integrating this we get W12 is equal to minus u. With the limit 1 to 2 we get is equal to minus into u2 minus u1, then multiplying the minus sign inside we get W12 is equal to u1 minus u2, that is the equation 2. We here got the two equations for the work done for the kinetic energy and the potential energy. Now the two equations are compared as the both are the work done in the path from 1 to 2, so we can equate these two equations. We get the by comparing the two equations, T2 minus T1 is equal to U1 minus U2, and rearranging the equation for the T2 with the terms of 2 and 1, that is equal to T2 plus U1, T2 plus U2 is equal to U1 plus T1, that is equal to T1 plus U1 is equal to T2 plus U2. Here T is kinetic energy and U is potential energy. That means the kinetic energy plus potential energy on the path point 1 position 1 and is equal to the kinetic energy plus potential energy at the point 2. Hence it is proved that the kinetic energy proves that the energy remains same at the 2 points, that means and that is constant. So at point 1 and point 2 the whole energy is conserved. So we can write conservative theorem of the energy of particle state. If that force acting on the particles are conservative, then the total energy remains conserved.
In winter, have you ever rubbed your hands together to make them feel warmer? What is happening when you do that? The kinetic energy of your moving hands is being converted into heat energy due to friction between the hands. This is an example of how energy converts from one form to another. Now, we are going to learn another property of energy. Energy cannot be created or destroyed. This means that although energy can convert from one form to another, the total energy in a system always remains the same. When we rub our hands, the kinetic energy is converted to heat. It is not destroyed. Similarly, the heat energy comes from the kinetic energy. It is not created. However, the sum of the kinetic energy and heat energy will remain the same. This important property of energy is called the law of conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed, but it can be changed from one form to another, and the total energy always remains the same. Let's perform a simple activity to understand the law of conservation of energy. To perform this activity, we need an eraser, a thread, and an iron stand. Let's start the activity. Tie the eraser at one end of the thread. Tie the other end of the thread to the stand like this. Now, pull the eraser to a point and release it. The eraser attached to the thread will start swinging back and forth continuously. Let's have a closer look at what happened in this activity. Let us mark the two extreme ends of the path of the eraser as A and B, and let's name the midpoint as C. In the beginning, when we pull the eraser from C to A, kinetic energy from our hand is converted into potential energy in the eraser. As we release the eraser, it starts moving and the potential energy stored in it changes into kinetic energy. When the eraser reaches point C, all the potential energy stored in it changes into kinetic energy and its potential energy becomes zero. Therefore, the kinetic energy is maximum at this point and the eraser is moving at its greatest speed. Due to this kinetic energy, the eraser continues moving forward. When it reaches point B, all the kinetic energy changes into potential energy again, resulting in zero kinetic energy and maximum potential energy. Due to this zero kinetic energy, the eraser stops momentarily and changes its direction. The above process continues as the eraser moves forward and backward. Let's discuss the conclusion of this activity. The total energy of the eraser remains the same as it moves forward and backward. The form of energy is changing as it is moving from potential to kinetic energy and vice versa. This shows that energy is conserved. But there's another question. Can you tell why the eraser eventually stops swinging after some time, although energy is conserved? What happens to its energy? You're right, Bubbles. Some of the energy of a system changes into unwanted energy. In this case, it will be the heat energy due to friction with air. This heat energy dissipates into the atmosphere and the eraser slows down and eventually stops when all the energy is dissipated. Do you know what would happen if you were to do this in outer space where there is no air? The eraser would go on swinging forever. The mechanical energy of the eraser would be conserved and there would be no energy dissipation as heat. Let's do an exercise. In the activity performed, can you tell which form of energy the eraser possesses between point A and C? Is it kinetic energy, potential energy, or both forms of energy? Between points A and C, the eraser has both kinetic and potential energy. While moving from point A to C, potential energy changes into kinetic energy. So potential energy increases. On the other hand, while moving from C to A, kinetic energy changes into potential energy. Time to summarize. The law of conservation of energy states that energy cannot be created or destroyed, but it changes from one form to another. In the absence of friction, there is no energy lost, and it can be observed that total energy in a system remains constant.
Now discussing the mechanics of the system of particles, we have studied about the definition of the particle and the point particle. Now we are considering the system of particles. The definition for the system of particle is a collection of particles. For a system of particles, two types of forces act upon the system of particles. The first is the external force and the second is the internal force. Single particle is a uniparticle, and the system of particles is a number of particles in one system. We can write or say that if we have a bird sitting on a floor, that is a single particle or a single system, and if there are a number of birds sitting on the floor, that is a system of particles in a group. So that we in classical mechanics, one work done for the one system or one particle is same as the same result for the system of group of the particles. The result will be the same, but for single particle that is converted into the sum of all the particles. If there is a single particle, there is a single force applying on a single particle, and if there is an internal force, there will be a single internal force applying on that particle. So if there is a system of particles, there will be some external force applying on the whole system as a whole, and there will be a internal forces present between the system of particles which are applying forces on each other. So first of all, writing the definition for the external forces: it is the force acting upon a particle of the system due to the source outside the system, that is Fe. The second definition is for the internal forces. It is the force acting on a particle of the system due to the interaction of the other particles of the same system. Considering the particles of the system, the external force acting on ith particle is represented by Fie. I means internal and E means for external internal force on the particle. Now for the internal forces, the internal forces on the ith particle. Ith particle means any particle in the system is represented by summation j is equal to 1 to n. That means that is for the system whole system of particle, that is equal to summation j is equal to 1 to n fji, where I and j are not equal, number of is not equal to j, and taking over all the particles in the system. This force is for the internal forces of the system. Summation j is equal to 1 to n j fji, and again if we take as all system of particles of a system and again taking a summation, we get that summation j summation I is equal to 1 to n into summation j is equal to 1 to n, that is is equal into fji. That is the equation for the whole system of particles. The above equation is for the ith particle in the system, and then below equation for with double summation is equal to the with the all system of particles in a. Now there is another example. Hello learners, in physics there are many examples for the internal and external forces we have to learn about. Forces are of two types: internal forces and external forces, which is very important. The bonds between inside the system preventing the object from breaking apart is called internal force. Gravitational force, kinetic force, electrical force, cooling force, all are these internal forces. External forces: force from applied from the outside from the superwoman bending the round bar is the external force. Applied force, normal force, tension force, friction force, air resistance force, that are the external forces. But how these internal external forces are produced? Importance of characterizing the force. Internal force is related to the ability of the obtaining force to change an object total mechanical energy when it is work done upon it. So we can say that mechanical energy is equal to kinetic energy plus potential energy. Mechanical energy is equal to kinetic energy plus potential energy. If we say that wheel has a mechanical energy constant and has displacement, when external force is applied but due to potential energy, the internal forces do not change the capability of change to total mechanical energy of the object. So we can say mechanical energy is constant. Only the potential energy tends to convert into kinetic energy, and kinetic energy turns into potential energy. But although the energy has changed, the total mechanical energy of the object will still remain constant, and that is because of the internal forces. So here is for the example of external forces has the ability to change the total energy of the object. Sometimes external forces are referred as non-conservative forces, as they change the total energy, see when total work is done on the body. One example, external for the total mechanical energy of the object will be changed. If not, if the work is positive, the object will gain energy, and when here are the example for the external forces, non-conservative forces. When work is done by the external forces, non-conservative forces, the work is either positive or negative. When is done on the system, that is positive. Then when done by the system, that is negative. In the same in the opposite direction, that is negative. These are the two examples for the external forces. Same direction, same force, same displacement, that is the positive work. Opposite force, opposite direction, that is the negative direction, that is the negative work done. Alright, that ends our lesson for today. But before we end, let us first summarize everything for the external forces. Difference between internal and external forces, and if external for the work done on the object can either be positive or negative work. That is the example for the internal external force. That is very important for the further topics we are going to do it. Hopefully that is the very interesting example for you. Thank you. Next we will take some references. Now in the last we have some references regarding your lecture. So if we summarize all the lecture, we have learned about the conservative field with the examples now, and work done in the closed path is zero, that means the conservation of energy, and then external internal forces and their examples. Thank you.